Okay. Welcome to Math317 Operations Research, probably lecture 23. So what I want to do today is we're doing things a little bit out of order because we had a visitor a few days ago and we did the beginning of fixed point theorems, contraction maps then. So we're going to circle back a little bit. A lot of times in math we are torn between what we can prove and what we want to prove. In an ideal world, we would have more than just an existence result. What would we have in addition to existence? Construction. And so what I want to do is I want to revisit some results you have hopefully seen in other classes, but you may not have seen proofs, and just talk a little bit about how you prove them. One of them we've already had to discuss in dealing with fixed points. So IVT, how many of you have seen IVT? How many of you could prove it right now if your life depended on it?
Are we allowed to use MVT?
No. If you could prove MVT without using IVT, then yes. So this is a great result, the intermediate value theorem. And it says, if f is continuous on AB, and let's say f of A equals A, f of B equals B, if C is between A and B, then there exists a little c in AB such that f of C equals C. Without loss of generality, let's assume A is less than B. Doesn't really matter, but just in terms of when I draw the picture, let's just draw the picture this way. So this is one of the key results. Whenever you see a theorem, you always want to ask what happens if you remove a condition. The theorem should either be false, or typically the proof is much harder. There's not that many conditions. If I remove continuous, it's okay, we'll just all look at you. So if I remove continuous, do you expect this to still be true? No, in fact, if you remove continuous, if here's A, here's B, here's A, here's B, you could imagine the function just goes like this. So we clearly need continuity. If you want, you could do some special cases. You could have A be positive, B be negative, and have C be 0. It's enough to do that one case. Okay? So the question is, anybody remember how you prove this?
You look at f of A minus f of B.
Okay.
And then you show that basically that it has to hit 0 somewhere.
Okay, so that's doing the special case. If you want, without loss of generality, we could assume A is.
Oh wait, no, sorry, that's.
If you want, you could assume.
That was the other way around.
Right.
Could you do contradiction?
So we could do contradiction, and so how would we actually make the contradiction happen?
Not 100%, but if I see the set blah 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 blah, then.
Yeah. Yes.
You could do like the real analysis, like A, B is like a compact set, and then there's some other, like, I should know this, but
Right.
it's like continuous functions of.
Right. So the question is, how much nuclear weapons do we need to do this problem? Do we have to drop an atomic bomb on it? Can we do it with a small?
We're going to contradict continuity if we don't have.
So we want a contradiction with continuity. That's the big thing we have. So f is continuous. So let's somehow violate continuity.
The continuous image of a compact set.
Oh, no, I'm sorry, no. This is, again, nuclear warfare. We don't want to have to do the advanced real analysis machinery.
Can we do a pre-image of an open set as open?
You could. I'm not responsible for what will happen to you from the classmates. All right? So let's try to look, if you want, without loss of generality, you can assume little a is 0 if you want, little b is 1. If you want, you can assume it's positive here, and you can assume it's negative here. This should remind you of the divide and conquer. And the question is just, how close can we come to proving this without going into real analysis? What point should I look at next?
In the middle.
Split it right down the middle, look at it 1/2. And so we'll take the special case where big C equals 0. We're just trying to show it has a crossing. If we can do this, we win. So if f of 1/2 is 0, we win. If not, it's either positive or negative. Let's assume it's positive. Maybe it's over here. Now where do we look? So we would look between 1/2 and 1. And if it's negative here, then we would look between 1/2 and 3/4. You're looking for that sign change. And so here initially we would have A0, B0 would be the interval 0, 1. And then A1, B1 would be the interval would be 1/2, 1. And then A2, B2 would be the interval 1/2, 3/4. And so on and so on and so on. What's going to happen every time we iterate? It's going to shrink by a factor of 2. In each interval is contained in the previous. So an plus 1, bn plus 1 is contained in a and bn. So if you've taken real analysis, you should be seeing or remembering a lot of the stuff you did in real analysis right now. What do you know about, so the terms an have to be increasing, or at least non-decreasing, and the terms bn have to be non-increasing. And what's nice is both of these are bounded. So an is a bounded, non-decreasing sequence. And then this is one of the properties of real numbers. If you have a bounded, non-decreasing sequence, what happens? It converges. So converges to, let's call it A star. And similarly, what's going to be true about the bn's? It's going to be a bounded, non-increasing sequence that will converge. Similarly, what do we know about A star and B star? They have to be the same. If there was a distance between them, every time we iterate, we cut the distance in half. So if A star is not B star, then eventually we're going to have a problem. Because each of these intervals, the length is decreasing by a factor by half. It'll eventually be smaller than that. And so we know A star equals B star. So the only real difficulty is, do you accept the fact that it is converging to an A star? What if we look at the limit as n goes to infinity of f of an? What should that equal? We want it to be 0. So what do we know about the limit of the function?
Oh, it's continuous.
It's continuous. So this is, we can move it inside. It's just f of the limit as n goes to infinity of an, which is f of A star, which is similarly f of B star. And this is just the limit as n goes to infinity of f of bn. So this is where we're using continuity. We have a sequence of points that are getting closer and closer and closer and closer and closer. On this side, we're always greater than or equal to 0. On this side, we're always less than or equal to 0. And they have the same limit. So I need a number that's both greater than or equal to 0 and less than or equal to 0. There's only one candidate. This implies f of A star equals f of B star equals 0. Because these ones over here are non-negative, and these ones here are non-positive. And so the only solution by continuity is they have to be the same. Okay, so this proves the intermediate value thing. Constructive or not constructive?
It gives you a way to narrow it.
So it gives you a way, so if you can evaluate the function, it does give you a way to find the point. It doesn't tell you immediately just by looking at the function f where that point is. Yes?
What do we mean when we say
does it give me a procedure to find a place where the input is set to 0? It does give me a procedure. In fact, very similar to linear programming, we can even do things with a tolerance. If I want to be within 1,000th of where the function vanishes, I can do this by iterating it enough times and getting this to be sufficiently small. All we need to be able to do to apply this method is to determine the sign of the function at an input. We actually don't need its value. We just need to know is the function positive or negative there. And so if you can determine the sign, this is actually an extremely powerful method. And so it is actually somewhat constructive. Okay, so this is the intermediate value theorem. After the intermediate value theorem, the next thing you look at is the mean value theorem. So the mean value theorem is one of the best theorems in calculus. Does anybody know what this special case is called? Roll's theorem. And in fact, Roll was, I believe, a skeptic of calculus. And it's funny that Roll is now best remembered for a calculus theorem. But there were legitimate concerns about the foundations of calculus. So mean value theorem is extremely important. Let f be continuously differentiable on AB, then there exists a C in the interval AB such that f prime of C is f of B minus f of A over B minus A. Okay. Constructive or not constructive? This is not constructive. This is just a point exists. And again, depending on how it's proved, you might be able to go through and construct a procedure to find it, but it's just an existence statement. The special case, Low's theorem, is when f of A equals f of B equals 0. And it's sufficient to study just that case. And this comes back to a trick we saw before when we were looking at fixed points. If I want to solve f of x equals a, this is not a fixed point problem. But I could find some new function g which is related to f, and if I can solve the fixed point of that, that's equivalent to solving f of x equals a. So the question is, if I can do Roll's theorem, if I can do this special case, can I do the more general case? So let's do Roll's theorem first and then discuss how to generalize this. So it's going to look something like this. F of A is 0, f of B is 0. If f prime of A is 0, is it hard to find a choice of C? If f prime of B is 0, it's also not hard to find a choice of C. So we might as well assume that the derivatives are not 0 at the endpoints. Without loss of generality, f prime of A is greater than 0. Without loss of generality, f prime of B is what?
Less than existence.
So can we assume that f prime of B is less than 0? I think all we can do is we can just say it's not 0. We don't know that one of the derivatives has to be positive and one of the derivatives has to be negative. Now, imagine f prime is greater than 0. Then that means the function is increasing like this. If we knew f prime of b was negative, we would know it's decreasing like this. So you want to then say there should be some point, and how would we prove that? So imagine we're in the case that f prime of b is negative. So case 1, f prime of b is less than 0. How can we conclude that there must be a place? Yes?
Well, we know the derivative is continuous.
The derivative, I'm assuming the derivative is continuous. So because the derivative is continuous, the derivative is positive here, the derivative is negative here. So by the intermediate value theorem applied to f prime, we're done. So that handles the case when f prime of b is negative. So now we have to handle the case when f prime of a is positive and f prime of b is positive. So here's A, here's B. Now, what does it mean for f prime of b to be positive? Where's the plot going to look like near B? So over here, I drew it. If it was a little bit before B, it was positive coming down. What does it have to be now a little bit before B? Negative coming up. Because if the derivative is positive, the function is increasing. And by continuity, if the derivative is positive at A, it's positive in a small interval. Similarly, if the derivative is negative at B, so this is case 2, f prime of B is greater than 0. So now it looks like this. Okay? I want to show that there's got to be some place where the first derivative vanishes. Yes?
Well, by IVT, we know that it has to equal 0 on the interval.
So we know that there has to be some place where the function vanishes.
And it has to be coming down towards it.
It seems like what happened.
Well,
Well, it could have multiple zeros. What if the function goes like this?
well, because it also, it could like touch and then go actually through later.
So real analysis is the worst subject in the world in terms of if you want something to hold with high probability, I can construct a counterexample. So the sine of x squared sine of 1 over x. How many zeros does this have in the interval 0, 1? Infinitely many. So when you say things such as, well, go to the first zero. There is no first zero other than A. You've got to be extremely careful. Complex analysis is the exact opposite. There is a huge, huge constraint to be differentiable. Differentiable in complex analysis is very different than in real analysis. In real analysis, how many ways can you approach a point for differentiability? 2. Okay. In complex analysis, if you want to approach a point, you can do a path like this. And if you want your function to be complex differentiable, it must be true for every path like this. I will risk going back to Calc 3 and multivariable calculus. You took your partial derivatives, df dx, df dy. Just because the partials exist does not mean the function is differentiable. And then there's a whole slew of theorems. What must be true about the partial derivatives in order for the function to be differentiable? Okay, so this is much more, it's a much stronger condition to be complex differentiable than to be real differentiable. And when you have that stronger condition, counterexamples like this vanish. They don't exist in complex analysis. But they do exist in real, and we have to be careful. All right. So we do know that it has to vanish, but we don't necessarily know anything. Is it possible that the first derivative is always positive? Well, if the first derivative is always positive, then the function is always increasing, and it can't come back down to b. So the first derivative must either be 0 at some point or negative at some point. If f prime is greater than 0 always, cannot vanish at b. Thus there exists, I don't know, an x star such that f prime of x star is less than or equal to 0. If 0, done, else we're now back into case 1. And that finishes the proof. So it's good to see proofs of things like the IVT and the mean value theorem and see how you do it. Yes?
I was trying to do.
Yeah. So if the first derivative is always positive, then we can't come back down to b because we know we have to come in from below. We can't be falling back down to b. So if the first derivative is positive, we have a contradiction. So the first derivative has to become negative at some point. If it even becomes just 0, if it never becomes negative, we don't come down. So it's got to be negative at some point, and then we can just use case 1. So the mean value theorem is extremely important. If you remember your Taylor series, this is a great way to start your Taylor series expansions. So if we look at what is the mean value theorem telling us, we have, say, f of x minus f of a over x minus a is f prime of c. So f of x is f of a plus f prime of c x minus a. So this looks like the beginning of a Taylor series. The difference is we're not evaluating this point at a. We're not evaluating f prime at a. We're evaluating it at some indeterminate c. And the question is, well, if we evaluated it at a, how close would it be? And then you can start to see how close. So if we do the first order Taylor series, that would be f of a plus f prime of a x minus a. You could see how close is it. And then the f of a's cancel. We'll get x minus a, f prime of c minus f prime of a. Let me just write that a little higher. So this would be less equal to x minus a times f prime of c minus f prime of a. How would you estimate f prime of c minus f prime of a? What could we do? What if I wrote this as x minus a, f prime of c minus f prime of a over c minus a times c minus a? Does this look like anything you've seen before?
Is that MBT again?
Yeah, it looks like the mean value theorem. So if the function is twice differentiable, this would be less than equal to f double prime at some new point, call it c2, and then it would be times c minus a if f double prime is, say, continuous and differentiable. And then this would be less than equal to x minus a squared times the maximum over C2 means we'll say AX of F double prime of C2. I shouldn't use C2, I'll just use and so if we now have some control over the second derivative, this tells us how good of a job the first order Taylor series does. And then you can lather, rinse, repeat if you want to do more and more terms. So this gives you a really nice application of the mean value theorem. This is a great way to lead into Taylor series. It's a great way to see how close you are. So even though we're only approximating it to first order, the error is really in second order. So if x minus a is small, it's being squared here. All right, any questions about the mean or the intermediate value theorem? All right, did we do the dot game Chomp in this class? Okay, so this is one of my favorite games. You can prove trivially that player one has a winning strategy, but it's non-constructive. And so this is leading us to our return to fixed point theorems. And for a lot of things, it's going to be terrible that we have non-constructive solutions. Right? Who is a baseball fan? Right? Something big is happening tonight. This could be the first time in World Series history that the home team has never won a game. It's never happened in a World Series before. Right now, the home team is 0 for 6. If you are managing, there's no tomorrow. It's today, it's do or die. There's been a couple of times in baseball history where some teams have had a wild card, 1-game playoff, and if you lose, you go home. If you win, and you continue. And some teams have elected not to use certain pitchers, and they've lost the game. And their fan base has been quite explicit about their views of these pitchers not being used and being well vested for the offseason. And it's an interesting strategy. When you only have one game, what do? Well, it's much easier in the World Series because after today, there's no more baseball. For the other teams, well, if we don't win today, we go home. But if we win, if we beat ourselves up so much, if we deplete ourselves so much, we might as well lose. Any tennis fans here? Okay, Eisner Muhammad. I believe I'm getting the names right. This was a classic Wimbledon game a couple of years ago. Professor Lepp and I watched it over several days between when we were teaching in department meetings. Wimbledon does not believe in playing a tiebreaker game to determine who wins a match. They'll do it for the first few sets, but they won't do it for the 5th set. You've got to win 3 sets. And so typically you win a set if you get to 6 games, but you have to win by 2. This game was finally won 71-69. It was absurd how long it went. And what do you think happened to the winner? They were destroyed the very next day. Now, they at least go into the history books as they won the longest game ever, so that's not bad. But by winning it in that fashion, they were destroyed for what came next. And so a lot of times you do make a strategic choice that I may not necessarily play my best to win right now, because if I win that way, I'm going to be so depleted for the next game, it's just not worth it. Today, for baseball, it doesn't matter. There's no more games. We had an interesting strategy in my son's baseball league where the number 4 seed played the number 1 seed in the semis before our game. And the number 4 seed was leading 6-0 after 4 2/3 innings, at which point their ace was no longer able to pitch. And they did not bring in their second best pitcher, they brought in weaker pitchers. It was 6-3 with bases loaded and 2 outs when they finally got the last out and won the game. But they deliberately saved their second pitcher, who threw nothing, so that if they made it to the finals, they would be available at full strength. We used our second best pitcher for 11 pitches in our semifinal game. We wanted to make sure we won the semis. It was a close game. And so there's a lot of good strategy and stuff like this. So this is all coming back to, do you have a constructive procedure or not? So one of the projects that people looking for something on the more theoretical side is Nash Equilibrium, which is a wonderful application of fixed point theorems in economics. And a lot of times you can prove that there is going to be an optimal strategy without knowing what that optimal strategy is. So here's the game of Chomp. You take a rectangular board, and the way it works is on your turn, you choose a dot, and you eat everything from that dot on up. So if I choose this dot, I would eat everything from here. If I choose this dot, I would eat everything from here. Okay? Everybody clear on what the rule is? So if I choose this dot, I would eat everything from here. On the next turn, if somebody chooses this dot, they would just eat those two. What do you think the goal is? To be the last one to move or not to be the last one to move? I'm sorry? Not. Imagine the goal is to be the last one to move. What would you do if you're player 1? Yeah, it's not a difficult game. So you can tell that the strategy, that the game has to be whoever goes last loses. And so what I'm going to do is I'm going to show that as long as the board is at least, say, 2 by 2, player 1 always has a winning strategy. So the claim is player 1 always can win. So for any board, there's going to be one person who will have the winning strategy. It is either player 1 or player 2. So there are two cases. Case 1, player 1 has the winning strategy. What should player 1 do in this case? Do it! Okay. That's still their motto, right? Okay. I wasn't sure if it was that or whatever China says. Alright. What would case 2 be? Player 2 has the winning strategy. So imagine player 2 has the winning strategy. What player 1 wants to do is they want to steal that winning strategy. So what this means is no matter where player 1 goes, player 2 has a way to win. So if you've already seen this problem, you can smile, but you can't answer. If you haven't seen this problem, where should player 1 go? Player 1 is eventually going to say, I want a do-over, and is going to take back its move. But where should player 1 go temporarily? Yes?
Bottom left corner and end of the pane.
So bottom left corner and end the game. No.
Maybe divided in half.
Well, so if we're doing dividing in half, that's a very complicated situation.
What do you mean, where should player 1 go? Do you mean what move they should do?
Yes.
So would it be the opposite of what Will proposed?
So which would be?
The least damaging move is close to the right as possible?
Yes, let's do the least damaging move. So if I go here, I remove as little as possible from the board. Now, player 2 has a winning strategy. All right, what should player 2 do now? So I don't know what the winning strategy is. Because I need to draw on the board, let's assume player 2's winning strategy is to go here. Okay? And now it's player 1's turn. And now player 1 says, oh wait, I'm so sorry. I didn't mean to go here on my first turn. I'm going to take it off. I'm going to take it back. I'm going to take back my move, and I'm going to go here on my first turn. And player 1 has just flipped positions with player 2.
What kind of game is that?
A game when you're playing with little kids. I should videotape some of the pool games I have with some of my kids, in terms of the number of takebacks that are sometimes allowed. So player 1 uses a takeback, and they use this to just find out what player 2's strategy is. So if player 2 really did have a winning strategy for no matter where player 1 started, if player 1 goes here, player 2 would have a winning strategy. Say it's here. Then all player 1 has to do is they just go there on their first turn. So this case can't happen. So there is always a winning strategy for player 1.
Doesn't player 2 have a winning strategy for what happens if player 1 goes there?
No, because we are making the assumption that player 2 has the winning strategy in this configuration. So that if player 1 goes here, there is a way for player 2 to force the win. And we'll say that that was going over here. So if player 2 goes here, then whoever moves here, once all of these and only these are eaten, has the winning strategy. So player 1 just steals that.
What if player 2's winning strategy is playing the corner?
Player can't play the corner. Because no matter where player 1 goes on their first turn, the corner is eaten. So it can't be that. Good point, but it can't be that.
Well, if player 2 has a winning strategy, no matter where player 1 goes, then doesn't it just cycle? It's like you say, okay, so then player 1 takes the second one, but then player 2, following that move, has a different winning strategy for that case.
No, because if player 2 has the winning strategy and going here, player 1 has just switched
Yeah,
parity.
so if player 1 now does that new one, is
No,
player
but
2 also has a winning strategy.
This
using that as a
contradicts this case happening. This case can't happen. That's the problem.
Okay.
It's like trying to analyze, what lecture you going to get tomorrow, given my love of the New York Yankees? I don't love the New York Yankees. That's not going to happen. Case 2 can't happen. It leads to a contradiction immediately. There is no way for this case to happen. Because if player 2 had the winning strategy, they would have to be able to win no matter where player 1 goes. So if player 1 goes here, if player 2 goes here, they can force a win. So if player 1 just goes there initially, they've now been able to switch positions with player 2, and they can now force the win. So this is a situation where player 1 has the winning strategy, but it is not clear what that winning strategy is. All right, so the last thing I want to talk about is we did a little bit of the triangle game when Professor Sue was here earlier, and he did Sperner's lemma. So we're going to lead up and we're going to do Sperner's lemma again. Before we do the full strength of Sperner's lemma in the triangle game, we're going to do a simple version. Yes?
Just to review fixed points, are we saying there is an optimal strategy if there exists a fixed point? I'm just curious about the connection again on fixed points and Nash Equilibrium.
So there are certain games where you can prove that there is a winning strategy, and the way that this is done is through the application of a fixed point theorem. And that fixed point turns out to be the winning strategy. It basically tells you how to play different things, how to allocate your moves. So we have not gone into that. I'm just saying that this is an application of fixed points. That if somebody's looking for a project that's more on the theoretical side, Nash Equilibrium is a great example. So I think Nash initially used the Brouwer fixed point theorem. I'm not 100% sure. I think that's the one he appealed to.
So could there still exist an optimal strategy without a fixed point?
Yes. But I'm saying there are many games where you can prove an optimal strategy exists by appealing to a fixed point theorem and then interpreting that fixed point as that's what you should do. That's how you should allocate your mixed strategy from the pure strategies.
And just because a fixed point exists does not imply it is an optimal strategy.
Well, I mean, you could have a fixed point when it's not related to a game.
I'm saying within the context of a game. If there exists a fixed point, that doesn't necessarily imply that.
It doesn't necessarily apply.
What if there's only one in a game? One fixed point. Is that still not implied?
It would really depend on how the game is structured. So here, all I want you to get from this is that we have some games that we can analyze and we can prove that there is an optimal strategy without being able to identify what that optimal strategy is. Nash Equilibrium is like that as well, where you can prove that something must be true. But depending on how complicated the mapping is, you may not know where it is. And so to some extent, it's almost useless. Now, if I had to play this game, I would probably want to go first. Yeah, I know whoever goes first has a winning strategy, but I don't necessarily know what to do. So we are eventually going to do Sperner's lemma. I want to start off with something easier. So for Sperner, we had a triangle. As mathematicians, we label 0, 1, 2. And we have labels that we want to put on. And down here, we can only use labels of 0 and 1. Over here, we can only use 1 and 2. Over here, we can only use 0 and 2. And then on the inside, we can use anything. And the goal is to either create or avoid a 0, 1, 2 triangle. And Sperner's lemma will show us that, in fact, it's impossible to do this. And the proof uses a really clever idea. What can you tell me about the number of 0, 1, 2 subtriangles? What kind of number is it? Yes. Oh, well, no, we're going to prove it's odd, but before you know that, what kind of number do you know? It is it's a natural number. And then you can argue as to whether or not 0 is a natural number. There's disputes on that. It's a non-negative integer. Then, as was remarked, you show that it's an odd number. And the smallest non-negative odd number is 1. So if you can show that the number of 0, 1, 2 triangles is an odd integer, there must be at least 1. So what I want to do is I want to end by looking at the simpler problem. So what if we looked at this in one dimension? So we start off, we label the two ends. We label one end 0, we label one end 1. And I want to construct some kind of labeling. So I'll put in a couple of dots. And in each one in the interior, I can put in either a 0 or a 1. And I want to show that I have to have an odd number of 0, 1 segments. And a 0, 1 segment is the same as a 1, 0 segment. The weaker thing is to show that there has to exist at least one segment that is 0, 1. So there's a simple proof that there has to be at least one segment that's 0, 1. If I want to try to prevent a 0, 1 segment, what do I have to label this? What do I have to label this? So if I want to prevent, this is like the prevent defense in football. At the end of the game, we want to prevent the 0, 1 from surfacing. I've got to just keep putting zeros from here. If I come from this direction, what do all the labels have to be? 1. And so eventually you get to one dot where it's got to be a 0 and a 1. It can't happen. So this proves that there is a 0, 1 segment. It doesn't prove that there's an odd number, but at least proves that one exists. All right. Let's put our labels in one at a time. So we start off with how many 0, 1 segments? 1. Now imagine you have a 0, 1 segment, or you could have a 0, 0 segment, you could have a 1, 1 segment. And a 0, 1 is really the same as a 1, 0. If I put in anything in here, what happens to the number of 0, 1 segments? It's the same. So if I put it into 0 or 1, it's unchanged. What if I put something in here? What happens? So if I put in a 0 or a 1, if I put in a 0, it's unchanged. If I put in a 1, so the parity is unchanged. If it was odd, it stays odd. If it was even, it stays even. What about over here? If I put in a 0, it goes up by 2. If I put in a 1, so again, it's the same as this. Parity is unchanged. So in fact, as you keep adding labels, the number of 0, 1 segments either stays the same or increases by 2. And since it starts at 1, it has to end at an odd number. Yes?
How would you show this reversely?
I'm sorry?
How would you show this reversely?
This is reverse. So whenever we have a 0, 1, if we put a point between them, it doesn't change the number of 0, 1 segments. I had a 0, 1 segment before. I have a 0, 1 here and a 0, 1 here and a 1, 1 here. I still have one 0, 1 segment. If I put in the 0, I would have no 0, 1 segment here, but I would have one 0, 1 segment there. So every time I put in another dot, I change the number of 0, 1 segments by either 0 or by 2. And so since I started at 1, I have to end up at either 1, 3, 5, 7. So you can do it inductively as you keep adding more and more points. So over here, if I was at 0, 0, I go from 0, 0 to either 0, 1, 0 or 0, 0, 0. In both cases, the number of 0, 1 segments has changed from the previous by 2. So as you keep putting in the dots, okay? So who wants to play me for an A+? If you can prevent me from getting a 0, 1 segment, I will give you an A+. And in fact, I will even let you make all the moves. I won't even play. Okay, so I'm assuming that there's going to be no takers. What could we do to make the game interesting? I'm sorry?
Add another side, make a triangle.
Well, we want to keep it just on the line. We have to change our definition of winning. So if winning is, if there's 1, 0, 1 segment I win, this game is boring. So one possibility is whoever has most. Is that game now interesting? Possibly. So one of the things is you always want to get into the habit of when you see something, well, how can I extend it? How can I generalize it? If it's boring, what could I do to make it interesting? So one possibility is whoever has more. Well, what if there's a tie?
Not numbered, both failed class.
I'm sorry? So we could have both fail the class, but,
So it's possible it does not number.
well, it depends on how many dots I have.
Oh, no. Odd numbers.
Is it on
Well,
the-
no, but what I'm saying is, 1, 2. So what if I have the following? I only have 4 segments, right? So if I do this, I would have 3, 0, 1 segments. So is it possible to have 2 0, 1s and 2 0, 0s?
Well, if
Or
the end
two
point is the opposite.
Oh, so you mean whoever has, so one person is counting just the 0, 0s and 1, 1s.
Exactly.
The other person,
So-
oh, okay.
So player 1 gets 0, 1 and 1, 0. Player 2 gets 0, 0 and 1, 1. So each person gets 2 configurations. So in this one, we have 3, 0, 1 segments. Is there always going to be, say with 4 segments, is one person always going to have 3? Is there any way to have 2 0, 1s and 2 others? Why not?
Because the 0, 1s and 1 zeros have to be odd.
Yes, because the number of 0, 1s has to be odd. So I know if I have 4 things, I know they can't be a tie. Right? Can't be a tie have an even number of segments. This is why I don't have to try to draw more configurations. I know the number of 0, 1 segments is odd.
It's only true if your number of segments is divisible by 4. If you have 6 segments, you could have a tie.
Ah, okay. Oh, good. So, good. If n is congruent to 0 mod 4. So if we had 6 points, now we could have a tie. Yes.
No, I might, okay, never mind.
Yeah.
Sorry,
So this would be a tie.
No, yeah, I was thinking for 12, it would still work because you have to get 6 and 6. But
Right.
it's not, yeah.
Right.
So mod 4 makes sense.
So on a 6, you have a possibility of having a tie. So one way you could try to modify this a little bit is you could say player 2 wins if player 2 has the same number. You let player 2 win if it's a tie. Or maybe player 2 wins if they're within 1 of player 1 or higher. Because you know player 1 has to have at least 1, 0, 1 segment. So maybe when you're trying to decide, should player 2 get the win, if player 1 has 5 segments and player 2 has 4, maybe you call that a win for player 2. How many of you ever played blackjack? What happens if the house and the player both have 18? Who wins? House. The house gets all the ties. So you could try to make this game interesting by doing something like that. And say maybe if there's a tie, we give the ties to player 2. Or maybe we have to subtract 1 from the score of player 1 because we know they have to have at least 1, 0, 1 segment. So this is something you could easily investigate and see, can you find a way to make this an interesting game? Who has the winning strategy depending on the board size? So if you want a theoretical project, here's another one. Can this become an interesting game? Is there a winning strategy for one of the players? If so, what is that winning strategy? And this is the mindset I want you to get. Whenever you see something, how can you push it? How can you create something new? So I've seen plenty of books that talk about just the standard version. Well, push it further. And so, in some sense, you get to now start handicapping and saying that player 2 maybe gets a little bit of a benefit because they're in the harder position. All right. This is a good place to stop.